Thank you, everyone. Then we are on talk 3 today, and our first presenter is Ron Bosworth, from Xenon Systems, and is going to talk about modern multi-tenancy solution for HPC and AI clusters supporting Kubernetes and machine learning operation. Whew. Well done. It's very long. Thank you, Ron.
It appears the clicker does not. All right, there's a trick to the clicker. I think there's a sensor over there. I'm going to need to stand at the back of the room.
No, don't do that.
All right.
Yeah, we'll remove that.
Off to a good start. Yeah, if we could just go back to the start, please. Wonderful. Hi, I'm Ron with Xenon Systems. Today, I would like to talk about some of our recent experiences working with GPU cloud platform providers to deploy multi-tenancy solutions, and the decisions we've helped clients make about the options available in this space. Thank you. During this talk, we'll review what multi-tenancy means and take a look at some typical solutions. We'll review the range of options available for hard to soft multi-tenancy and the trade-offs involved as you move along the scale. I'll run through some interesting large cloud provider examples and how we've seen storage integrated into these environments. And finally, we'll cover some of the challenges and lessons learned along the way. What exactly is multi-tenancy? In general, it's when you have multiple groups of users sharing the same system with a degree of logical isolation from each other. Sometimes it's multiple users within the same team, collaboratively running workloads that may need to communicate with each other. This is typically what you would see with classic HPC batch systems, which you will find at many universities and supercomputing centres. Or you can have multiple teams within the same organisation who operate independently, where it's preferable to have some level of isolation between the teams. On the other hand, when you have multiple customers sharing the same system, you will want each customer to be strongly isolated from each other, which is the usual case for public-facing platforms such as cloud providers. So what are our options for implementing multi-tenancy architectures? You could simply have dedicated hardware for each tenant. So each tenant is physically isolated from one another. We see this with clients who are seeking large amounts of dedicated infrastructure. They'll work with a partner who can implement the infrastructure as a single tenant, anything from several racks or perhaps a whole data center all to themselves. On the other hand, you may have multiple clients in the same environment with dedicated compute and storage and a shared network. In that case, the system can be logically isolated on the network level. Then there's virtualization, which enables compute to be logically isolated while still sharing the same physical hardware. Typical virtualization platforms include those based on Linux KVM, like OpenStack, OpenNebula, and Proxmox. There's also Xen-based options with Xen Server and XCP-ng. And there's also VMware and Hyper-V. In a similar way, containers can also be used to logically isolate workloads on the same hardware using container engines like Docker or Podman, scaling up to large multi-node Kubernetes clusters. So how do we decide which options are the most suitable and what are the trade-offs for each approach? There's the question of hardware, management and utilisation. Thank you. We could be looking to manage several types of compute node, different compute to RAM ratios, along with different types of GPU. How are these systems divided between tenants? How do we go about, for example, allocating a single GPU out of an 8 GPU node to a tenant, or perhaps a fraction of one GPU? There are solutions available to cater to any of these scenarios, but each comes with its own set of trade-offs. When we look to divide GPUs into fractions, we can increase utilisation by efficiently slotting jobs into available resource gaps, though this level of granularity tends to come with a high management overhead. We can consider allocating individual GPUs to a tenant, but like with fractional GPU allocations, we're sharing the same server hardware between multiple tenants. This means we need to consider how the system is managed and how, not yet, and how we can ensure fair quality of service and system security. Who's responsible for managing the operating system and security updates? If the provider is aiming to allocate entire nodes to a client, then perhaps the responsibility for node security falls to the client, which would reduce the platform provider's management overheads. It all depends on the level of abstraction and involvement the platform provider is aiming for. There's the performance impact of running virtual machines on top of bare metal, which is quite low thanks to hardware acceleration, but it's still worth considering. And for application management, perhaps the platform provider is aiming to support a full service application deployment stack. If that's so, then how are software dependencies and asset management handled? Who's responsible for securing which components? When it comes to planning the type of multi-tenancy you want to implement, it can help to think of it as a spectrum from hard to soft multi-tenancy. The hard side of the spectrum is more focused on hardware level controls, moving from separate physical networks and compute to shared network hardware with network virtualization and separate compute, through to shared hardware and separate compute virtualization. Beyond that, there's containerization, including Kubernetes, which can use namespaces and virtual networks to isolate tenants from another. Then there's application level controls, software managed processes, workflow allocations, and software as a service multi-tenancy platforms where tenant access is managed using identity and role-based access controls. In general, it comes down to balancing the required features against the management and configuration overheads. Let's take a closer look at implementing hard multi-tenancy at the network level. We recommend this approach for larger cloud providers who are looking to onboard multiple clients. In this architecture, there are several different network types to consider. There's the north-south network, which is designed to handle traffic between the compute nodes and the outside world, or any other supporting systems like data storage. This network is typically high-speed Ethernet and supports RDMA over converged Ethernet, known as RoCE, to enable very low latency data transfers to and from locally connected systems. There's the east-west network, which is designed to provide high-speed, very low latency, non-blocking communication between the compute nodes. This network can be high-speed Ethernet with RoCE support, or perhaps InfiniBand to enable distributed parallel compute jobs that require a large amount of inter-node communication, such as when training a large language model. And finally, there's the out-of-band network, which is designed so the cloud providers can connect to all switches, storage, and compute nodes to enable easy configuration and maintenance. This network is typically gigabit Ethernet. Usually, only the platform maintainer has access. Across the network, traffic is controlled using VLANs, route leaking, ACLs, and firewalls, and in the case of InfiniBand, the network can be segmented using partition keys. These networks can be provisioned manually, configuring the switches, manually by configuring the switches, semi-automatically using config as code systems like Ansible, and fully automatically using software-defined networking and cloud management tools such as Netris, ANA, or RAFE, just to name a few. The software-defined networking solutions are great for keeping up with configuration churn expected when onboarding tenants, as the network configuration can become quite complex, involving EVPN, VXLAN, BGP, and a leaf-spine architecture with configurations of at least 11 network links per node, 8 for the east-west network, 2 to 4 for the north-south network, and 1 to 2 for the out-of-band network. Configuring the network manually is not recommended, but if you must, then we recommend leaning on tools like Ansible to assist with automating and testing as much as possible. Automation tools like Ansible are key to building a consistently redeployable network, which enables you to use services such as NVIDIA Air to build a digital twin of your network so you can test and verify configuration changes before they are deployed live. If you're using a software-defined networking solution, be prepared to build the network configuration from scratch, as importing an existing network is usually not recommended or supported. Let's take a closer look at Netris, which is a cloud provider-style network automation tool designed to work with NVIDIA's Cumulus Spectrum switches. In this diagram, we can see the north-south network above the nodes, which is also known as the TAN, or Tenant Access Network, and the east-west network below the nodes. Netris has an API to support integration with other control and monitoring systems that you would see in a typical NVIDIA AI factory deployment, such as BCM and NetQ. It also supports NVIDIA Air for simulating and testing digital twin environments. Using Netris really helps manage the large number of links involved, especially in the east-west network, which is designed to be non-blocking and therefore requires many more links between the leaves and the spines. Building a non-blocking network with today's link speeds typically means each node has 8 links of 400 gigabits connected to the leaves, which requires 4 links of 800 gigabits from the leaves to the spines. As you can see with this 32-node example architecture, the number of links quickly adds up. Moving up the stack, we have RAFE. RAFE provides a service for orchestrating Kubernetes clusters. This service works well when combined with Netris for network-level tenant isolation. On top of that, you can use RAFE to configure soft tenant isolation at the Kubernetes level. Users can use the web portal for self-service deployments of machine learning pipelines and other applications like Jupyter Notebooks. The portal also keeps track of finance and billing information, along with other features that you would expect to see in a good GPU cloud platform. On the left, there's a high-level system architecture diagram showing how everything can be connected. We can see some nodes are running VMs in Kubernetes, then there's bare metal deployments, and the base command manager, BCM nodes, to handle bare metal provisioning. On the right, we can see how RAFE organizes tenancies and instances, with instances grouped by workspace and workspaces grouped by organization, offering plenty of flexibility. Then there's the question of data storage, which can be an interesting challenge too. In most cases, you want a large, powerful storage system with isolated namespaces per tenant. Network access to those namespaces is enabled by using isolated virtual IP addresses pools to manage traffic at the network level. There's additional security controls that can be implemented at the protocol level and integrations with identity providers for each tenant. Other features typically include encryption, both in-flight and at rest, quotas, and quality of service. There's several storage solutions available that support multi-tenancy, plenty of details to consider. So to summarize the challenges, multi-tenancy can be difficult due to the large management overhead and system complexity of sharing network and compute infrastructure. Manual network configuration becomes unsustainable quickly. Automation can help with this, especially when onboarding tenants and validating configuration changes. Switching to a software-defined network solution will likely require a clean slate. There's a variety of approaches to implementing multi-tenancy, and many of the approaches can be combined. Carefully consider your requirements and plan for the future. Changing direction could be challenging to manage. And be sure to pick the right solution and partner for the implementation. Thank you for your time.
We are a little late, but we have a few minutes for questions. If any of you have any question that you would like to ask Ron about. If you don't, I have one. About upgrades and updates, which is always, I think, a tricky part for us. Any advice on that that you would like to give? Because when you have, all the tools, all the GPUs, and the different Kubernetes, how do you think we should manage that?
So updates and upgrades, always tricky. The idea is to migrate workloads where you can, organize downtime and plan for the worst where you can't. With systems like Kubernetes and virtualization, fortunately migrating workloads is much easier these days.
Automation, it helps, isn't it?
Absolutely.
Thank you very
Thank you.
much. Anything else for Ron? No? Thank you very much, Ron. And now we have Marco de la Pierre, who is going to talk about an hybrid Slurm-Kubernetes platform to integrate AI workload in HPC infrastructure, and is from Do It Now. Thank you.
Thank you. Hi, everyone. Thanks for being here today. So I'm going to talk to you about a solution we've been developing and working on. Yeah. No, I've broken it. Wrong button. Okay. I'll try to only move forward then. All right, so I'm going to talk to you about a solution we've been working on in our R&D team to provide a hybrid deployment for our customers that mixes together HPC and AI workloads by mixing Slurm, like schedulers and Kubernetes. So a few words about our company first. We're doing now, so a global HPC consulting and services company, active all over the world with offices in multiple European countries and New Zealand as well, here in Auckland, and staff in other countries as well, including Australia, where I'm based. As I was mentioning, we do provide HPC services all the way from design of solutions to installation, managed services, and training and R&D as well. We are active across a wide range of industry verticals, including life sciences, so pharma, but also manufacturing, energy, racing, and both in the private sector and academia. We've over 200 clients all over the world. Next, please. One notable aspect I wanted to mention is that we are active contributors to a number of open source projects in the HPC and AI space. Some examples here, such as, which I'm going to talk and refer to later as well, such as Open on Demand, Easy Build, Women in HPC, and a number of European projects. But now let's focus on our main topic for this talk. So AI has entered now in a significant way the world of scientific computing. And seen from a perspective of traditional HPC, traditional HPC users were already running AI workloads in traditionally HPC infrastructure with little variation, still mostly scheduler and batch-based workloads. But we now have this significantly growing cohort of users that are AI native. They didn't have any exposure to HPC. So they are coming in with different requirements compared to what the HPC world was used to. So there is a lot of request and demand for easier and more interactive platforms to engage with. A lot of focus on being able to use graphically enabled tools and interfaces for the workloads. A relatively less awareness and focus on performance and efficiency for their workloads. Here I'm talking from the user side, which can be actually a challenge because of the large scale of the workloads that AI basically requires. And this is where I'm going to spend a few more words on. So when you say graphically enabled cloud native AI workloads, then here we're thinking about Kubernetes, which was a technology that was already popular in the corporate and business IT world, with a lot of points of strength in the specific context. When coming to the realm of scientific computing, it comes with actually quite a lot of advantages. For example, applications portability, thanks to the usage of containers, but also, as I was mentioning, the availability of graphically enabled interfaces that make the life of users easier, and also ease of integration with CI/CD pipelines and the like. And we've seen this increase in the use of Kubernetes. For example, if you have a look at the top 500 systems, this is probably from a couple of years ago, Kubernetes basically represented 10% of the pie of schedulers in the top 500, so quite significantly, basically the second most common and popular scheduler after Slurm, which is rather telling. So really making it into the heaven of the HPC world. And I mean, as you all know, NVIDIA acquired REANNZ last year, just to give the idea that there is indeed significant and major uptake of Kubernetes-based technologies in the scientific computing and AI world. So with that in mind, as I was mentioning, coming from an HPC-focused world, we identified that there is actually this gap in awareness and relevance of the efficiency and performance aspect when running this type of workloads. So when looking at the standard approach for Kubernetes deployments, coming from HPC, we noticed that there were some weak points. For example, the lack of native compatibility and native capability to expose, for example, CPU topology, memory affinity, efficient distribution of tasks across large nodes, thinking of MPI jobs here, but also capability in terms of scheduling jobs. Here I'm thinking about, for example, the advanced scheduling policies in Slurm, such as enable for backfilling, preemption, and the like. All of these aspects that in a native Kubernetes environment are not really ready out of the box and available to users. And also adding, for example, if you think about all of the potential in the optimization of the actual applications that you use to run the workloads themselves. All of this has a huge impact on the efficiency of what you're running, and then on the return on investment of the money that you're spending for setting up and running your AI workloads. So it's actually quite significant. It's an aspect that we think that should be talked more about and more crucially implemented appropriately in the actual solutions we design for our users and user communities. So just a few questions to drive the next slides then in describing our solution. So how can we address these needs of new users in relation to the existing HPC landscape of solutions? How can we satisfy their demands without compromising or minimizing the impact coming from performance and efficiency point of view? And then how can we keep developing solutions that get more and more mature and improve on the existing? So here, what I'm going to describe then is a hybrid solution which brings together, which basically starts from our well-known HPC kind of design based on a job scheduler such as Slurm, the most popular in the space, and blends together with a Kubernetes approach. So from a high-level perspective, what you can imagine is basically just a cluster of compute nodes where each node is capable of running both batch jobs via Slurm in this particular design and Kubernetes. And then the solution is then capable of exposing this compute power to the users in a friendly way and actually in a flexible way as well, so offering command line for traditional HPC users, hardcore ones, but also graphical interfaces such as Open on Demand, which comes from the modern approaches in HPC, but also Kubernetes native interfaces such as kubeflow and the like. So this, I'm describing here then this flexibility in how users can use and consume the platform by keeping under the hood a unified, consistent infrastructure that integrates this hybrid way of managing the actual compute. And then, of course, once you have that, you need to be able to integrate all of the other components, in particular storage, in a way that works for both the Kubernetes deployment and the Slurm deployment. So with this type of design, where you are able to run both Kubernetes and Slurm workloads in the same infrastructure, you get the benefit of a single bare metal to manage. So no duplication, less cost in setting up and running. So cost savings as well. By coming from HPC, and I'm going to describe more aspects in a few slides, we want to keep this performance focus. So at all levels of the design, being able to give the accent and maximize the performance of the solution. And then we, again, coming from HPC, we're capable of offering additional services that we've been offering to the HPC clients for quite a long time, such as cloud bursting and unified software stacks and so on. As Ron was just mentioning before, of course, multi-tenancy is very important. One word here. So in our current implementation, here we're talking about HPC-grade multi-tenancy. So we're sitting basically in the middle of the scale that Ron was describing. This is important to mention. Our team is working on that to offer more flexibility across the scale that Ron was describing. Another important caveat, right now, this solution is a granularity at the node level, and again, we're working to improve this granularity to go at the sub-node level. How do we achieve, let's focus for a moment at the level of the compute node. So how do we achieve this coexistence of Slurm and Kubernetes workloads? Well, it is important to mention we're letting Slurm drive the way. So Slurm is leading the management of the resources, in that it is Slurm that evaluates basically the business of the cluster. If there is an underutilization from a Slurm perspective, so few batch jobs running, then Slurm is able to release some nodes and let then Kubernetes enroll them under its management. And then, on the other end, when the time comes where Slurm actually needs more resources, then it will basically request Kubernetes to release some of the nodes when available, and then it will resume the operation of the Slurm daemon to get those nodes back into the HPC batch scheduling realm. And that's how we're able to balance the usage of the two platforms on the same bare metal infrastructure. So this is from the hybrid perspective. Now I want to spend a few other words on other aspects that are complementary but also very important. Just a few words about management of this type of setup. Our solution is basically cluster manager agnostic, so it can work with Werewolf, MAS, BCM, and we're also testing it with newer solutions such as OpenChami. Normally, we do recommend Werewolf. It's just because it's the one technology where we see more flexibility in terms of capabilities. But as I said, otherwise, it's quite agnostic. This is one important aspect. So user experience. So as I was mentioning, we've been championing the usage of Open on Demand as the single graphical user point of contact for the whole platform. And this is what we are keeping to offer to our new HPC/AI users. And there will be a talk by my colleague Yves on Thursday, focusing specifically on open on demand. Of course, this comes aside of offering more Kubernetes-oriented solutions such as Kubeflow, MLflow, and the like. But we believe open on demand can really be the single pane of glass where users can go to consume any service on this type of infrastructure. And here is the other aspect I was highlighting before a few times, so performance. As I was mentioning, we want to keep this focus on performance at all levels. So first of all, on the applications perspective. So we are also champions in the adoption of the EASY scientific software stack, which is a European project which we have been contributing from the start as a company. EASY provides a catalog of optimized scientific applications that have been, so that means shipping binaries, multiple binaries for each application, optimized for multiple CPU and GPU microarchitectures. This enables the ability to deploy and port your workflows out of the box on any sort of infrastructure with maximum performance, reducing the human cost in importing your workflows and ensuring reproducibility. And again, there will be another talk by my colleague Yves tomorrow, specifically focusing on EASY. So this is from the applications performance point of view. As I was mentioning, it's also important to think about the scheduling performance, and that's why we believe it's important to maintain a Slurm HPC scheduler component in this type of platform, because at the moment it's really this solution that enables maximum and optimal utilization of the hardware bare metal. When it comes to having to move to Kubernetes native workflows, we've been researching the optimal solutions for maximizing the scheduling on the Kubernetes side as well. At the moment, our recommendation goes for Q. This is what we deploy for our customers. But we are actually investigating other options and technologies as well, such as the Kai scheduler that NVIDIA acquired last year. And finally, again, with an accent on performance, we highlight the importance of having reliable and capable solution and platform for the monitoring of the cluster and job efficiency, in which case we currently design our own in-house solution. So this is where we stand right now. This is just a future-looking slide. So just to suggest, as I was mentioning, our team keeps working, our R&D team keeps working on several aspects to continuously improve this type of solution. And just to mention an example, one way that we're moving this forward is by investigating podless and containerless solution to bring the bare metal even closer to our users' workflows with technologies such as KCP. So to conclude, I tried to describe to you how our solution can address the needs of both HPC and AI users by combining together Slurm and Kubernetes, by exposing all of these services in a unified pane of glass with open on demand, how we can maximize the performance of this type of platform at all levels, from the application down to the cluster, by combining the easiest of the stack, capable scheduling solutions, so Slurm plus Q, and proper efficiency and cluster monitoring. And finally, as I was mentioning, this is an ongoing work with a lot of R&D involved to move this forward in the future. That's all from me. Thank you.
Very much, Marco. It's very interesting. Is there any question for Marco? Oh, yeah, Kyle, go for it.
I like that. So you say you're running both Kubernetes and Slurm on the same bed or not. Have you ever investigated, but running Slurm on Kubernetes?
So we've been investigating a few solutions. We've also been exploring, solutions that are being designed by other parties, such as Slinky by the Slurm team and so on. In this case, what we wanted to do is really to develop ourselves the minimal working setup. And then our R&D plans will entail adding more functionalities and expanding on the flexibility. So at the moment, our focus has been on this hybrid. But we are also actively covering other possibilities. And yeah, Jordi may have something more.
Yes, I think so. Do you want?
No, that's okay. So the thing is that the main complexity that we are facing in Kubernetes is lack of CPU binding and memory fusion. And without that, you don't have HPC. You have the H is lowercase. So that's why we come up with this.
That's why you're running side by side with the same.
So if you need HPC, you use Slurm, pure Slurm. And if you need more kind of AI or any other reason that is not heavily important on the high performance, efficiency, you use Slurm. It will come. Eventually it will come. But for now, we are in the transition.
In this one, do you think they're going to, since NVIDIA's now got their fingers in all these pies, Slurm, Kubernetes, and all that, do you think they're going to start making more memory fidelity, that kind of thing?
NVIDIA bought Skeleton, which is the company behind Slurm development. So something is coming, for sure.
Yeah, it would be definitely interesting to see.
Thank you. We have another.
Marcus here. Do you differentiate when you say AI about the scientific computing with AI optimization bit, which is probably more traditional HPC, versus running large language models where you want to utilize, all the VRAM and pretty much every device GPU available? Does it change the performance significantly, and can you switch from running that one mission-focused thing for one group to spreading the joy to a whole bunch of multi-tenancy? Sorry.
So yeah, that's the idea. I mean, it's really to provide a solution that is capable of covering everything, and the idea is to raise attention towards maximizing performance. So every workload that really needs performance, we want to make people aware that HPC scheduling at the moment is still the best solution. That's why we want to offer it in our unified design. Whereas anytime there is no really a choice, but you need to run a Kubernetes native workload, then you can move on the other side of this platform. So it's basically a way to offer the users the whole spectrum while making them aware that performance is important. And so they should aim for design their workflows in a way that can run with maximum performance. And as it was suggested, of course, the development in these technologies is ongoing. So hopefully, we're going to get to a stage where Kubernetes will bring in all of the required functionalities to provide native performance natively as well. But while not there yet, we believe this hybrid offering is the best way to maximize performance.
Thank you very much, everyone. Thank you, Marco. It was really interesting too. All right, and the next talk we have is, we start with Richard Hoare from Sempre Technologies, and then Jordi Blasco from Do It Now on quantum computing without quantum.
Thank you. Hi, my name is Richard Hoare. I'm the CTO of Sempre Technologies. We've been providing high-performance compute platforms for customers for quite a few years now. We also partner with Do It Now for a lot of the implementations. We have been investigating into quantum computing for a little while now, and it's still probably not quite ready, but we need to be ready. And so, next slide, please, sorry. Okay, so just a brief overview. You've all seen the chandelier with cryogenic chambers, and so these are more traditionally towards superconducting. But there are other companies coming out, like PSI Quantum, which use photonics, and they're building their appliances are actually more aligned to fitting them within a normal data center rack, so they'll be in the same footprint and also require less cooling than the previous. That's cool. With the sorry, I just lost my train of thought. That's cool. With some of the other vendors that are not on here, like the likes of Microsoft and NVIDIA, And so NVIDIA, Jensen Huang stated that that he sees quantum computing being ready for real-world applications in around 20 years' time. So he's actually pushing it right out there, versus the CEO of Google came out and stated that he sees this happening within the next 5 years. And so that brings a few issues which we need to do, because customers' data is key for us, and the security of the data is key for us. Next slide, please. And so, as you know, quantum computers will have the ability to break a current model of SSL encryption. And so the current Willow computer from Google has 1151 QPUs in it. By 2033, they're going to have 100,000 qubits in it. And so a quantum computer with less than 1 million qubits will be able to decode SSL. And so we're working with vendors at the moment, Dell Technologies, on software, hardware, and other vendors, to make sure that their platforms are actually ready for when this does occur. And so next, in Q2 of this year, Sempre is releasing a platform that will have post-quantum cryptology resistance built into it. And so we're already looking at that and actually deploying these sort of solutions already, and to make sure that customers are actually safe when that does occur. The customer, so one of the vendors up here, PSI Quantum, which I just mentioned about before, they are working, they're actually got a big deployment base in Brisbane, and they're actually working with 5 of the big universities in Australia. And so those universities are already creating courses and content for students and getting people skilled up onto that. And so this brief today was for Jordi to provide on quantum emulation, because we feel that's a way for New Zealand to actually start and actually move forward rather than being left behind. So hand it over to Jordi.
Thank you so much, Richard. So we can switch to the next slide deck. So I'm Jordi Blasco, and I'm good at keeping people awake. So, this is it. Oh, look at that. Yeah. So a bit of so this Mark already explained this. I can just move ahead on the next one. So we are a consulting company, a services company. We don't sell hardware. We don't sell software. We don't sell cloud. Having said that, we have installed 5 of the top 500. We have 20 clients at the top 500. And we partner with people like Sempre, so they can deliver the hardware, and we do what comes after that. Okay. So global organization, we have around 160 people scattered around the world. And this is a bit of the context, the background story of Do It Now. Why I'm explaining this? Why providing this context? We provide other services for pharma industry, so we are quite strong in that vertical, and in other verticals that will embrace quantum computing as soon as it's available. So if you see the investments coming from the stock market and so on, you will see that companies like Pfizer, Roche, Merck, they're investing a lot in quantum. Why that? Because they are going to be one of the earliest adoptions. So we are doing a lot of things in Europe, as you know, so we are behind 4 European projects, but we are also here. What are we doing in the quantum space, on the real quantum space, not on the emulation? So we have provided, so there's a supercomputing center in Europe, the Supercomputing Center of Galicia, that they purchase a quantum random number generator. Is any in the audience doing Monte Carlo simulation? Raise your hand. No one? That's devastating. Okay, so Monte Carlo simulation, very important thing, okay, really. It's used for many things, from molecular dynamics to fluid dynamics to a lot of things, okay? You try to do this on a traditional HPC environment, and it will consume a reasonable time. In a quantum random number engine like this, it gets done really, really fast. So the supercomputing center got this nice and shiny device, and they hire us to evaluate the level of entropy generated by this device and compare this with traditional HPC environment. And it turned out to be really, really successful, but we discovered things that the vendors, they were not aware. So we put in place a monitoring system. We developed a monitoring system to evaluate if the system needs to be calibrated and when this needs to happen. So we also partnered with Kilimanjaro. We are now facing on the third installation. So this is the first quantum computer, this is the second one, and the third one is going to be, guess which color? Green, yes. And the ceiling will be, so the ceiling will be removed. Well, it's removed already, so this is a slightly older picture. The new pictures will be available sometime soon, and you will see the ceiling, it's gone. So this is the Barcelona Supercomputing Center. It's sitting in the chapel, in the old chapel where the Mare Nostrum 3 and 4 were located. Now Mare Nostrum 5, it's a lot bigger, that cannot fit in that room. It's sitting in a building next to it, and now that chapel is hosting the quantum computers. So we partnered with Kilimanjaro to deliver this interaction between the classical HPC and the new era, the quantum computer. So this is how we see the future of quantum, hybrid. So not everything will fit in the quantum computer. You need an actual HPC system able to fit the data and then doing the initial assessment and an initial workload, and then eventually you go to the quantum computer. So many of these people, of you in this room, have been working in GPU computing for a while. And if you remember the very beginning, you had your regular code. You put this in the performance analysis application and tool, and you see this loop here consumes 80% of my runtime. I'm going to move this tiny region here to GPU, and then boom, the application runs a lot faster. But how much time? So imagine that you have 20% of regular code now running in a traditional CPU, and then the 80% running in the GPU. But what is happening now with this workload where 2/3 of the time it's running on a CPU, and then just 1/3 in the GPU, you are wasting 2/3 of the CPU time because you are not using the GPU. GPU, it's expensive. Yes, we all know. Do you know how much it costs? Millions, literally millions and millions of euros. So one of those devices, 50 million price tag, and so if you want something bigger, you will need to pay a lot more. So optimizing this in a way that the Slurm consumes this in a reasonable way is the tricky part, and this is what we are doing. Now, all this fancy stuff and all these millions of dollars, are you ready for that? So if you remember AVX instruction set when they arrived, Intel made a kind of a massive campaign of code modernization. Do you remember that? So it was quite a strong push on that. It was just introducing the SIMD instructions in a regular code that you already are very knowledgeable about. But here we are changing this radically. So getting aware of, getting ready for this, it will take time. It will take probably decades. Getting started on this is what we are trying to promote, because this is coming. There is no way to stop it. So this is what is happening currently. So there is a lot of very smart people over there that they are doing really, really amazing stuff. So first first system in being developed, that was 2011 with D-Wave. Have you got stock from D-Wave? Probably you got a stock from NVIDIA, so $1,000 or $10,000 10 years ago, now you are a millionaire. This is going to happen, so invest in those companies. So Rigetti, all those things are going to boom eventually. Nobody knows when, but it will happen eventually. Ion-based commercial quantum computer already in the market, IBM showing that this is a reality, and then just across the Tasman Sea, a company, Quantum Brilliance, was creating a quantum computer at room temperature. Only 2 qubits, but there is no fancy stuff that you require to lower the temperature to pretty much 0 Kelvin. And just a few months ago, Google claimed that to create a chip nearly suitable for error correction, which is awesome as well. So this is happening in less than 10 years time frame, or around a decade. It's accelerating to a new reality. So this is the what I'm trying to explain in this slide. It's this. So we have a large variety, as Richard mentioned. So there are a lot of companies doing quantum computing, creating a lot of variety. Which one is going to be the one? We don't know. Probably multiple of them. Okay. What about the quality? Well, yeah, we know. So error correction is a challenge, and it's going to be a challenge still. And what about the availability? That's the real challenge. So as a researchers, consuming and using that infrastructure, it will take time or a lot of money. So what are the options? Basically, working on the emulator realm, you don't need a fancy quantum computer. You can use your own laptop or a supercomputing center with a lot of GPUs, and you can use an emulator. Otherwise, you can go to the cloud, AWS Bracket or any other things. There are a lot of quantum computer companies that they are offering access and a cloud-alike service. Or you can go to a public institution or a supercomputing center and use a real quantum computer. Obviously, this is extremely expensive or really hard to get in. This is a lot cheaper and easier, and probably before you use this, you want to prepare yourself with that. So, and I believe I have very small time, like 2 minutes or something like this. So this is, I'm going to do my best. So I have a lot of slides to go. Okay, so this is an example. So this is a quantum volume calculation with 100 shots. Basically, what we are trying to do here is to see how many qubits I can incorporate in an emulator. And so this is the number of qubits, and this is the second. And I can see here, let's zoom in on this section. And so I can see that with 28 qubits, GPU, which should be green nowadays, is providing quite a substantial performance compared to regular CPU. So that's why when we talk about the quantum emulation, NVIDIA is there, and AMD GPUs are there. The problem is memory. So if you see here, so it's grouped at this stage, and this is because it's limited by the memory. How much memory we can use? Still have 1 more minute? Okay.
We'll have less questions.
Okay. So in traditional computing, you have zeros and ones, and quantum, you have a lot more. So how much you have? Let me give you the formula. 2n, and this is not a multiplication, it's an exponent, okay? Times 8. If you want double precision, 16. So this means that you go to a regular laptop, 29 qubits, nice, eh? You go to Mare Nostrum 5, and you get 45. You go to the top one in the top 500, El Capitan, with 5.4 petabytes of memory, and you get 48 qubits. Okay, just letting this to work. So just to wrap up this really quickly. don't fall in those hypers or haters of quantum computing. So there is, when you search on internet, you will find a lot of things like, and even really important people in our field, like Jensen from from NVIDIA, or people from Google, or from or from IBM. Okay, so we're in this transition period. So there's a lot of uncertainty, but there's a lot of investigation going on. So 20 years, I doubt it. I think it's going to be a lot closer. 2 years, 1 year, that's no way. Okay, but it's going to be something between. In the meantime, the reality is that there are no codes that are already available or ready for the quantum era. And this is where what we are trying to motivate and to promote in this kind of events. The good thing is that emulators use exactly the same infrastructure that you have currently in your HPC or supercomputing centers. The same infrastructure that you have for HPC or AI clusters is exactly the same infrastructure that you can use for an emulator. And that's me. Thank you so much.
We have 1 minute. Any question for Jordi about quantum computers? Without? Yes, go for it.
What industries and use cases do you think
What industries?
use cases do you think it's going to play best in first? What are the first?
Pharma industry?
Yeah.
Pharma.
What industry do you think is going to crack first in quantum? Might be most useful. We're actually using it in the industry. Where will it be used?
So not sure if I understand the question. So what industry in the
What industry? So obviously like cryptography or so quantum safe networking that you can do. We have a bit of that. But what other industries do you see quantum working in?
Yeah.
Where will you apply first and successfully?
So well, so you have. I just highlighted a case study. It's the quantum random number generator. So if you are in an industry that consumes Monte Carlo simulations, or you need kind of a very diverse aleatority numbers, so this is perfect for you. So that goes on finance, that goes on finite element, molecular dynamics. So yeah, there are a lot of things that currently can consume that. And you can use this on the cloud. So and there are a lot of companies that are consuming this. So it's there, but it's one application, one use case, right? So moving forward, the drug design, drug discovery really fits well with what we can achieve relatively soon in quantum computers. So those 3 quantum computers that you saw in the picture, or the 2 that you saw in the picture, the third is being installed as we speak. One of the primary usage will be in the drug design, drug discovery. And then in other sectors, there's a lot of things are going on machine learning and artificial intelligence. So usually in most of the science, you need double precision, but ML and some other aspects, you only need a single precision or half precision. So this works really well because the amount of memory that you need for a system like this, it's a lot less, and it's less requirement in the error correction and so on. So yeah, so not sure if I'm able to answer your question, but yeah.
Thank you all of the speakers, Ron, Marco, Richard, and Jordi. Thank you all.